Good morning friends. In the last lecture we talked about the stationary signals, and just to give you an example, we talked about this example, but we will recapitulate none the same, that any rotating or reciprocating machines will have an inherent time period for operation of one cycle. For stationary signals we understood that different machine components do generate stationary signals. So, let us recapitulate that once more. Associated with the operation of such machines, we have an inherent time period for the operation of one cycle. So, if the time period of operation is capital T, that will be related to the shaft RPM as 60 by N. So, in case of 4 stroke engine, this will be in fact 120 by N, because 2 cycles of the shaft rotation will lead to 1 cycle of the combustion. So, the associated fundamental time period will be 120 by N. So, the operating frequencies will repeat with a periodicity of T or with periodicity of multiples of T. Certain processes like in 4 stroke engines, you will have 2 cycles of the shaft of the crank shaft. If once it completes 2 cycles of rotation, only then the combustion will repeat. So, therefore, it will be multiples of T, but then the forces which originate from the basic operations of the machine will therefore have frequencies of the order 1 by T, 2 by T and 3 by T. So, they are all going to be integer multiples of each other or harmonics of each other. That is the fundamental point. And if there is now a structural resonance occurring at any of these frequencies, then you can expect large vibration and hence large noise. So, what we are trying to show is that 1 by T, 2 by T, 3 by T, all of these are basically related to the engine RPM N, right. So, N being the engine RPM, the reciprocal of the time period is all related to the engine RPM. So, all of these forcing frequencies, in other words, are linearly related to the engine RPM or the crank speed fundamentally. So, just as I said, there is the difference in 4 stroke engine as compared to the others is that the combustion cycle will repeat with 2 T, and therefore, you will have 1 by 2 T as the fundamental frequency, and all integer multiples of this fundamental frequency will be present in any noise and vibration signal. Similarly, for the shaft carrying gears, when the gear tooths will meet, then the fundamental frequency will be the angular speed into the number of tooth. This is dictated by the time period that is taken for 2 consecutive engagement between 2 consecutive gear tooth pair. This is called the gear meshing frequency. So, the gear mesh frequency is given by angular speed times the number of tooth. And these frequencies are in fact colloquially termed as orders. So, when we say that there are certain orders of your noise and vibration signature in the signal, then we say that these are the fundamental frequencies and these are the harmonic frequencies which are present. So, in order analysis, typically what we are interested is to find out what is the nature of the forcing that happens at different RPMs, like the combustion process, for example. Again, for different speeds of the crankshaft, it is going to change. So, typically in acoustic analysis, order analysis is pretty important. Just a quick recap for the non-stationary signals also. So, as we said that the character of the signal does change with time, and that is why it is called non-stationary. Typical examples are music, voice and engine rev ups that can happen. So, in such cases it will be erroneous to decompose these non-stationary signals into different frequencies. So, as a part of one of your assignments, what you will be asked to do is you will be asked to take FFT and inverse FFTs. So, you will see that for a stationary signal, if you take Fourier transform and then inverse Fourier transform it, you will get back the same, you will recover the same signal, whereas that will not happen in case of non-stationary signal. So, this is one way in which you can quickly identify the difference between stationary signal and non-stationary signal. In other words, what that means is that when you are dealing with non-stationary signal, you should not use Fourier analysis technique without applying your mind. You can use different versions of Fourier transforms like short term Fourier transform, but the routine vanilla application of Fourier transforms has to be avoided. So, there are more specialized tools such as wavelets and STFT which are employed, and I think I talked about this graph in the last class also. So, I will not recap that part. Carrying on, we were till now talking about tonal noise, that means single frequency type of situation, or we also talked about frequencies which are happening in a discrete manner. When we talked about order analysis, for example, there were multiple frequencies that we are talking about, but these frequencies were harmonically related. But then there are cases where we contain where this acoustic signal contains all the frequencies spilled over a certain interval. We say it is a broadband noise if the frequencies contained in the signal is in an interval of about 1 kilohertz or so, then we will call it as a broadband noise, and the examples being fan noise and wind noise. If it is spilled uniformly from right from the limits of audibility, that means from about 20 hertz to 20 kilohertz if you might wish, then it is called a white noise. So, white noise is an example where there is absolutely no correlation between the values of the signal, and if there is no correlation, then that means there is all the frequency contents are spilled onto the spectrum, and that is why we call it as white noise, right. So, therefore, this is an example of white noise, and typically these kinds of processes, what we did the other day in the MATLAB illustration process, if you remember, when we just asked MATLAB to generate us the a few samples of these random numbers, and we played that out, that was creating a hush hush sound typical of let us say the sound that you are hearing of the AC right now. It is also having a quite a dominant component of this white noise. Typically when you have flows in without any resonance effects, not the whistling sounds, but without any resonance effects, if you have these kinds of flows, you will have white noise. Whereas if you have some tonal noise embedded within the flow, you will have a narrow band noise. For example, flutes. When you have flutes, depending upon the location of your finger, which hole you are closing, you will have different resonance conditions, and associated with those different resonance conditions, you will actually have a dominantly tonal noise, but yet there will be some frequencies spilled around that tonal noise, and therefore, we would rather call it as a narrow band noise, but a dominant contribution coming from a tone. So, these narrow band noise as opposed to broadband noise will have a very small frequency interval, wherein the frequency content is non-zero, typically of the order of 20 hertz or so, whereas when we say it is a broadband noise, it is a much broader frequency interval, wherein it has a dominant contribution. So, even the whistle that we blow out, if you typically take a sound signal and do a proper experimental analysis, that sound will have a narrow band effect. Air conditioning now, if you have here, gone to any power distribution system place where there are lots of transformers, you will see here a typical buzzing noise. So, that will have dominantly a tonal impact, but then it is not exactly a pure tone, there will be certain frequencies which are spilled around that pure tone. So, this is a broadband noise for you. The contributions are unequal over the entire frequency level. Broadband noise does not mean that all frequencies are equally present, that happens only in the case of white noise. Whereas, in a narrowband noise, you will see that the dominant region in the frequency spectrum happens to be located in a smaller interval as opposed to broadband noise. And when we do discrete frequency analysis, we are just approximating individual frequencies, we are not approximating all the frequencies, we are talking about each and every frequency, probably multiple such frequencies can be analyzed, but we are not going to analyze a continuum of frequencies, that is the crucial point of differentiation. Okay, so, with this sort of precursor, we are now in a position to get ourselves convinced that it makes sense to make the reduction from time to frequency domain. It is actually a matter of simplification in terms of the mathematics of the problem, but at the same time we are convinced that there are lots of application areas in machine noise, wherein we should be able to do a good analysis staying with a frequency domain based analysis. So, the way to go forward is that we will actually do the analysis for a single frequency, but then we understand if we can do it for one frequency at a time, we will just have to repeat for all other frequencies, right. So, the discrete frequency analysis, for example, is not a big deal. We just have to, we will show you the procedure how to analyze for one frequency, but if you know what is the procedure to analyze one frequency at a time, then you might as well do it 5 times to do this analysis for 4 or 5 different frequencies. You have to simply write a loop in your computer program in your analysis methodology such that the loop repeats over the entire frequency points of your interest. Okay. So, with that, let us begin our analysis for harmonic waves. So, by now we are convinced that for steady state or stationary acoustics, the signal can be decomposed into a number of frequency components, and we also know that the governing equations of acoustics is a linear partial differential equation. So, therefore, we bring about the harmonic assumption, which will come in a moment. So, the analysis can be simplified by investigating each frequency component separately. Rather than trying to analyze all the frequency components simultaneously, we will take the divide and rule approach, wherein we will analyze each frequency component separately, and then we will recover the total solution simply as a superposition. So, that is the harmonic assumption for you. So, the harmonic assumption is hereby stated in the following manner. So, all quantities of interest, typically our quantities of interest are acoustic pressure, acoustic velocity, acoustic density, and later on we will come across acoustic intensities also. So, all the physical quantities of interest from here on will be assumed to have harmonic dependence, and once you say it is a single harmonic dependence containing only one frequency, then we can understand that it can be expressed in a complex exponential form or a phasor form. That is what we did in few lectures back. So, from here on we will say that, for example, our acoustic pressure quantity, which we understand was a variable dependent on 2 independent arguments, namely x and t, but from here on the time dependence will no longer be arbitrary. The time dependence will be frozen to be that of complex exponential kind, such that we have only a single frequency or a simple harmonic solution for p x. Same holds true for velocity, same holds true for density. Whatever we wish to analyze, it will be analyzed in terms of this fundamental feature, that any variable of our interest will be boiling down into this form. The variable will be dependent on the spatial location, but the temporal dependence will be simplified in the form of a complex exponential. That is the harmonic assumption for you. So, with this harmonic assumption, let us return to our acoustic wave equation. As usual, we will start with the simple case of one dimensional acoustic waves. So, the one dimensional acoustic wave equation, if you recall, was derived to be this. There is a typo here, it has to be T on the right hand side. So, d2 p dx2, or rather del 2 p del x2 is 1 by c square del 2 p del t2. Okay. So, the t has to come in the right hand side. I had copied pasted it, which is why the x has come back again. Okay. So, that is the acoustic wave equation, if you recall, and with the assumption now for the harmonic assumption, as we said in the last slide, we are going to replace this function p x comma t to be p x into e to the power I omega t, and when you make that replacement, del 2 p del t 2 will be minus omega square p, and you bring that on the other side and you get this form. Please note that between these two steps there is a partial derivative sign or the del sign in the first step, but it has been reduced to d sign or the ordinary derivative. That is because after incorporating the harmonic assumption, there is only one argument to p, that is x. So, therefore, there is no question of any partial derivatives, there is only ordinary derivatives that appear in this equation. Note that this is a second order linear constant coefficient differential equation. You would have studied that in a course on how to solve this type of system in a course on, let us say, vibration, and it is exactly the same way that you will solve this equation. So, I am not going in pretty much details about this solution. So, the solution of this ODE will be of the form of e to the power I plus or minus omega by c times x. E to the power I omega t has already been invoked. So, the time dependence is e to the power I omega t, the spatial dependence has got to be square root of omega square by c square, which is plus or minus omega by c, and it comes with a I sign, because when you transfer it on the other side you will get a minus sign. So, since I assume that you have a background in a vibration theory, so you will know how to solve this kind of second order constant coefficient differential equations. So, this brings to the solution in this form. So, what we are seeing here is that the solution is given in its functional form as e to the power I omega t plus or minus omega c times x, right, omega by c times x, together with an undetermined constants a. A will be an undetermined constant which has to be determined, right, but fundamentally there are two solutions, e to the power I omega t plus omega by c times x or e to the power I omega t minus omega by c times x, right. So, with these two solutions you can superpose or you can combine these two solutions in any combination and get the solution to the partial differential equation made possible. So, therefore, this quantity omega by c is technically called the wave number. It is actually a single word, wave number, it is not I should not have given space for it, k is called wave number. So, I will just make that correction here. So, k equals to omega by c is called wave number, okay. And we have got p x comma t to be a e to the power I omega t plus k x plus b e to the power I omega t minus k x. Okay. So, this is the form of the solution that we are having, okay. K being called as the wave number. Okay. So, you may recall that what we had earlier was that we had, when we did not invoke the harmonic assumption and we solved out the wave equation in its complete arbitrary form, the solutions were f of tau plus x and g of tau minus x, but tau is Ct. So, we had the solution in the form of f of Ct plus x. Now, f of Ct plus x does conform to this form where you have e to the power I omega t plus omega by c x. Please note, the crucial thing to identify is that the coefficient multiplying the argument t should be c times the coefficient multiplying the argument x. So, we have exactly here the same attribute, that is the coefficient multiplying x can be identified to be omega by c and the coefficient multiplying t is identified as omega. So, therefore, the coefficient multiplying t is c times the coefficient multiplying the variable x. So, f of c t plus x does conform to a functional form after invoking harmonic assumption as a, where a is an undetermined constant. It does not depend on time or space or frequency or anything. It is merely a constant with the value of which has to be determined, multiplied by a complex exponential, but the argument of the complex exponential has got to be exactly c t plus x. Okay. C t plus x and omega t plus omega by c x or omega t plus k x for that matter does not make any difference. We had identified f of c t plus x to be a backward travelling wave, right. So, now that f has got a special form which is complex exponential form, the physical character of backward travelling wave does not change. It is just that the profile of the wave, earlier we had illustrated these functions like some triangular wave functions, but now we are specializing this to harmonic functions or sinusoidal functions, right. So, this complex exponential form is going to lead us to a backward travelling wave, and similarly you will recall that the other solution was g of x minus tau, which could also be written as h of tau minus x, and now if you replace tau to be c times t, you are going to get h of c t minus x as the other solution, and this was identified to be the forward travelling wave solution, and this forward travelling wave solution h of c t minus x after invoking the harmonic assumption could be written in this other form. So, if I now choose the minus sign associated with this solution, I get to see I have a time dependence coefficient which is c times the coefficient of time of space dependence, which is omega by c. So, the plus sign is associated of this general solution is associated with a backward travelling wave, and the minus sign associated with this solution is associated with correspondingly the forward travelling wave. We have understood in great details forward travelling waves and backward travelling waves even without invoking the harmonic assumption. But now specializing for the harmonic assumption, the physical picture remains unchanged. It is just the form of the solution is no longer triangular, but rather it is harmonic or it is sinusoidal. So, I will show you a few forms to illustrate the same. But before I do that, you will note that when we had a complex exponential, we said that if omega is the speed of the phasor, then the phasor comes back after one cycle at after a time of capital T is equals to 2 pi by omega. Now, we have the phasor to be dependent on both time and space, that is the only complication we have. So, associated with the time dependence, you have a time period of 2 pi by omega. Associated with the space dependence of phasor, you will have a similar quantity which is called lambda or the wavelength, which exactly by the same analogy will be defined as 2 pi by k. So, the time period is the time after which the quantity is repeating, wavelength is the space after which the quantity of interest is repeating. So, the time period is 2 pi by omega, because omega is the coefficient associated with t, the coefficient associated with x is k. So, associated with that the periodicity in space this time will be 2 pi by k, which is given the name lambda and technically qualified as wavelength. So, wavelength and wave number share the same relation as time period and angular frequency. So, in other words, you now have a situation when we are dealing with harmonic waves where you have a phasor both in time as well as in space. So, that is a very crucial insight which we will elaborate upon, but before doing that, let me just quickly plot out a few graphs to enable you to have a visualization of these harmonic waves. So, if I take for example e to the power I omega t minus k x, right, and plot it for t equals to 0. So, I am only plotting the real part. So, at t equals to 0, this fellow does not live, you only have minus k x, and then you take the real part of it. So, it basically means it is a cos k x type of a plot, which is what this shows, right. The blue curve that you see here is the response or the acoustic pressure profile at time t equals to 0 associated with this function, right. Now, if I increase the time by quarter of the time period, right. So, it is the time has moved ahead a little bit by quarter of the time period. Capital T in my notation denotes the time period. Time period is 2 pi by omega, and after a quarter period of time, if I make the same plot, then I will see that I am going to get this red plot. In other words, this point has moved here. The plot is always with respect to x. So, at consecutive time instants, I have plotted in red, in blue, red, black and magenta, right. So, what we see is that each of these points which are at what we say as constant phase points. So, the maxima point for example, is moving in this fashion. The minima point similarly from the blue plot, if you can identify, this is the point of minima. So, this minima point is moving in an identical fashion, right. Therefore, visualize this. If we now plot all these, generate all these plots in a loop and have a visualization of this corresponding to an animation, we will see that it is as if this profile is moving in the forward direction, right. But please note that at each instant of time there is a periodicity associated with the response, whether you talk at t equals to 0 or at t equals to t by 4 or at t equals to t by 2 or finally at t equals to 3 t by 4, every time you do get a repetitive plot, right, and this repetition in space is going to be called the wavelength, right. So, I have just taken some arbitrary numbers for generating these plots which are given here. So, the point is that after a time duration of 2 pi by omega capital T, that is, which is not shown in this plot, I have plotted only till 3 t by 4, I have left the last quarter, I have not plotted it simply because I felt that the graph was getting too cluttered. So, the fact is that after a certain time duration, what will happen, which the time duration corresponding to the time period, which is 2 pi by omega, if I generate this plot, this blue form will exactly hit this form, right. So, this point would come back here, which means it will be exactly superposing. So, the profile would have travelled exactly a wavelength distance. Remember, wavelength is associated with the snapshot at a fixed time. So, at time t equals to 0, if I see what is the wavelength, this is from this point to that point, right. What happens after a fixed after the time period capital T equals to 2 pi by omega, this point would have exactly come and it would have occupied the point here, which means the story is going to repeat, somewhat like a mega serial. It will keep continuing on the same track, it will keep repeating the same story and it will be almost like a never ending situation. So, after the time duration 2 pi by omega, the profile would travel a distance which is equal to 1 wavelength, and therefore, in this fashion also we can see that the wave speed c, we already realized that c was the wave speed even without harmonic assumption, but even with the harmonic assumption that idea is reinforced that c wave speed is going to be omega by k. This is very important relation, you should never forget that the angular frequency and the wave number, that ratio of it is the wave speed, right. Okay. So, similarly you can talk about the backward wave this time. So, backward wave is obtained by plotting this form of the solution. So, again we generate the plots for different time instants, starting with time instant 0, t by 4, t by 2, 3 t by 4. What has not been done is what happens exactly at t. At exactly capital T time, which is corresponding to 2 pi by omega, this blue point would have moved exactly here, right. So, it is going to be exactly the same idea, but in progressive time instants, this time if you plot, the blue comes to red position, the red comes to the black position, the black comes to the magenta position, and in the next cycle the magenta would again come to the blue position. So, the entire story would be repeated after a time of capital T, which therefore, it would actually overlay with this blue plot. So, there is no point in plotting that blue blue curve anyway. So, after the time duration, again we will see that this profile would have travelled a distance 2 pi by k, which meant that the wave speed is again omega by k. But please note that this time the direction of wave propagation has reversed. The idea of periodicity of this profile remains the same. It is the same periodicity. I have generated the plot keeping those numerical parameters to be same. The same periodicity is obtained, which is what is called the wavelength. So, these are, remember, snapshots taken at a particular instant of time. At each instant of time there is a spatial periodicity which is the wavelength, the value of which is 2 pi by k, and it turns out it can be marked off in your figure to be this. So, that is associated with the wavelength concept. Okay. So, carrying on forward, now what we introduce is this idea of a space and time phasor. We already know what is a time phasor. So, if we look at any point, so let us look at the first column of this figure, right. So, this plot is generated for x equals to 0. This is a phasor plot as opposed to a graphical plot. So, we already know that any point in space will have only harmonic dependence with time, and that harmonic dependence is of the form of e to the power I omega t. So, therefore, it can be represented as a rotating vector, the rotational speed of that vector being exactly omega being the angular speed. So, if we plot out the form, or in a phasor form, if we depict this story at any point, we will see that at consecutive instants of time it is going to occupy different positions and basically giving the feel that the vector is rotating in the anticlockwise direction with a speed of omega. This is true not only for x equals to 0, but any arbitrary x that you take, right. But the only difference between the time direction and the space direction for a forward travelling wave is that these two phasors are rotating in the opposite sense, and that can be understood from this equation also, because the sign associated with the spatial coefficient is flipped. For a forward travelling wave, you see the sign comes with a minus sign, right. So, omega by c for a forward travelling wave is associated with a minus sign, whereas the coefficient associated with time t always remains positive omega. So, therefore, the phasor associated with time rotates counterclockwise, but the phasor associated with space, if it is a forward travelling wave, will be minus k, and therefore, it will rotate at the speed k, but in the clockwise direction. If you are dealing with a backward travelling wave, the situation is less complicated, both the phasors are rotating in the counterclockwise sense. The time phasor anyway always rotates in the counterclockwise sense, but this time the space phasor also associated with the phase phasor, the coefficient is plus k, and therefore, the space phasor rotates at k at a speed of magnitude k, but sense counterclockwise. So, I have taken up the more complicated case here, which is that of a forward travelling wave. So, in that case we see that the space phasor is rotating. So, in space what we take is that now what we are dealing with is time remaining constant. So, the snapshot profile is as you would view in one row, instead of having a column viewpoint, which is the viewpoint of what happens at different times at a fixed point. If we adopt this viewpoint, that it is a snapshot, which means what happens to different points at the same instant of time. So, for the same instant of time, the different points will also be harmonically related, which means that there will be a phasor, but the phasor this time will be rotating in the clockwise sense at a speed of k, right. So, therefore, when it covers 2 pi by 8 k, which means pi by 4 k, it has gone 45 degree in the this time in the fourth quadrant, right. Again in the next next point in space, now I should not say time instant, but it is the next spatial point, which is taken as x equals to 2 pi by 4 k, in other words pi by 2 k, the point would have, the phasor would have come at minus 90 degree location. Please understand, if I adopt a viewpoint in this direction, then I can feel that the phasor is rotating in the clockwise sense, whereas if I adopt a view in this direction, I would feel that the phasor is rotating in the counterclockwise direction, right. But please note that once I have any arrow given, I should be able to generate the plot at consecutive instants of time as well as consecutive spatial positions. For consecutive instants of time, I have to rotate the phasor in a counterclockwise direction. For consecutive instants of space, I have to rotate the phasor in the clockwise direction at a speed k. Now, let us see how, therefore, to generate the location the phasor orientation for this point, all that I have to do for different time instants is that I have to rotate it counterclockwise. So, at the next instant of time, it will be rotated counterclockwise. Again the time has been so chosen that it will rotate by 45 degree, but this time it is in the counterclockwise sense, which is why this position will come to this position, in the next instant of time it will come to this position, and finally here. So, this story keeps happening in all of these arrows, right. So, what finally happens therefore, or the moral of the story is this: if you look at any diagonal position such as this, right. So, you are going to see that the orientation of the phasor is unchanged, right. For example, this orientation or this orientation. So, all of these space time points. So, whatever happens at x equals to 2 pi by 8 k t equals to 0, same is the orientation of this phasor at x equals to 2 pi by 4 k, time is equals to 2 pi by 8 omega. So, the orientations being identical. Same thing happens here, this x and this t will have the same orientation. So, that means the point is going to travel each of these distances at these time instants, right. So, the nature of the solution is going to just get communicated progressively at different spatial points as the time evolves, right. So, that is the important point. That is what we understood even without the harmonic assumption, when we generated different plots or through the method of characteristics, we understood that whatever happens at a particular x and t gets conveyed along the characteristic lines. So, exactly the same picture is again reinforced by this phasor plot, wherein you see that all these space time points have identical phasor representation, which means the phase associated with this wave remains identical at different space time x comma t. So, this is what is called a space time phasor. So, earlier we were only drawing a phasor with time, now we are drawing the phasor with respect to both space and time, and this is a very interesting insight, and you would do well to learn this aspect. So, the time phasor rotates at counterclockwise speed, whereas the space phasor rotates at speed k, but in the clockwise sense. I should have written that space phasor rotates at speed k, but in clockwise sense. Yeah, that is the next bullet. Space phasor rotates in clockwise sense for the forward wave, but for the backward wave it will rotate in the same counterclockwise direction, and I have just explained to you the reasons why we are differentiating between these two different kinds of wave, that is the forward wave and the backward wave. Okay. Carrying on, we will now introduce to you another important concept of impedance, and in particular this is called characteristic impedance associated with a travelling wave. So, by now we are convinced that a harmonic travelling wave can be represented in this form. It has an undetermined constant and together with a complex exponential, the argument of which is omega t plus or minus k x. The minus sign is associated with the forward wave, the plus sign is associated with the backward wave. So, I am doing this problem together for both forward and backward wave, right. Now, as we said, our harmonic assumption at that time, we said that all quantities of interest have got to depend harmonically, right. So, not only the pressure, the velocities also will depend harmonically. So, therefore, the velocity has also now been reduced to this harmonic form. So, the temporal dependence is no longer explicitly made. The temporal dependence is implied to be complex exponential. In fact, what we will do probably from the next classes, that we are not going to write this explicit temporal dependence. Hereafter all the time dependence is assumed to be e to the power I omega 2, right. So, temporal dependence will be implied to be complex exponential. So, that part does not change. The spatial dependence is what we are going to solve out, and we are going to write that explicitly. Anyway, at this point we are writing it in full detail. So, the velocity, acoustic particle velocity u can be written in this form as u times e to the power I omega t. Please remember, this is the particle velocity, this is not the velocity of the wave. Okay. Remember, each particle simply oscillates about its own position at a certain velocity, but the wave keeps moving forward with the velocity c. Okay. So, if you recall the Euler equations connects the acceleration of the fluid particle with the pressure gradient. For a one dimensional situation, the pressure gradient is just del p del x and the acceleration is rho 0 del u del t. We have already seen that the convective acceleration term does not bother us, because we are dealing with extremely small oscillations or extremely small fluid flow velocities, and therefore, these things will just be the convective acceleration terms will just get reduced to 0. So, all that we are left with is just the time derivative of u, and now since we have assumed the form of u to be the form of u in time to have a dependence of e to the power I omega t. That means, when you take the time derivative of this function u, all that you are going to get is an I omega popping out of the u itself, right. So, again that is something you would have seen even in vibrations class, that I omega times u is du dt. So, that is what I have written here, and similarly del p del x now can be worked out, and when you work out del p del x for the forward wave, it will be minus I k x, right, and when you work out del p del x for the backward which comes with the positive sign, it will be plus I k x, right. But together with the minus sign that is sitting here, the signs will now be reversed. So, for the forward wave it will be plus I k p, for the backward wave it will be minus I k p, right. So, we have got this relation relating pressure and velocity for both forward travelling plane wave and backward travelling wave. So, we define a quantity which is called impedance, and the impedance as per definition is acoustic pressure divided by acoustic particle velocity, right. So, what we have is for a forward travelling wave which comes with a positive sign in this equation, you will have this quantity to be rho 0 c, and for a backward travelling wave we will have it to be minus rho 0 c, right. And the fact that there is a flip in sign should not sort of bother you, that is because for a forward travelling wave the direction of wave propagation is opposite as compared to the backward travelling wave, and as a result the direction of the particle velocity will also be opposite. So, the particles will not travel in an identical fashion between the forward wave and the backward wave, the particles will have exactly the opposite velocity. So, the pressure to velocity relation will be in magnitude it will remain the same, but in sign it will change, right. So, if you have a forward travelling wave, the pressure and velocity will be both bearing the same sign, because the wave is going in the forward direction. So, velocities will also be inclined in the forward direction when the pressure is positive, right. When the pressure is negative, remember we are talking about acoustic pressure, which means we are talking about pressures over and above the mean atmospheric pressure, right. So, wherever there is a region of build up of pressure, there we have a build up of acoustic velocity also. So, the velocity is directed in the positive direction. So, in other words, when the particles are trying to go in the positive direction, there is a pressure build up, right. Similarly, when the particles are for a backward travelling wave, when the particles are trying to go in the negative direction, there is a pressure build up, which is but natural, because we have these two waves travelling in the opposite direction. So, accordingly impedance is for travelling waves will be is found right now, which is of the value rho 0 c, but the sign of the impedance term has to be carefully understood. The sign for the positive travelling wave or the forward travelling wave will be plus, whereas the sign of impedance associated with the negative travelling wave will be minus. Okay. And in particular, just to we will keep seeing that the impedance will, this term impedance will appear in very many different contexts, right. But remember, the impedance calculation that we are doing on this slide is associated with the impedance of a travelling wave. So, to make sure that we are talking about the impedance of a travelling wave, we call this impedance as a characteristic impedance. Okay. So, that is why this rho 0 c is actually the characteristic impedance. So, as I argued that particle velocity will always be in the direction of wave propagation. I mean the relation between the particle velocity and the direction of wave propagation is what causes this change in sign. Please note that let us say for a forward travelling wave, particle velocity is always in phase with the acoustic pressure, right. Wherever there is an acoustic pressure build up, there is a velocity build up also. Similarly, wherever there is an acoustic pressure build up, there is a negative velocity that is coming out through this mathematical formula, but you will identify that this negative velocity is actually in the direction of the wave propagation, right, because you are dealing with a backward travelling wave. For backward travelling wave, it comes with a minus sign. So, when you see that there is a pressure build up, this formula tells you that the velocity is going in the negative direction, but the negative velocity is actually the direction of the travel of the wave. So, that is the direction of travel. So, in other words, if you interpret this formula physically, what it means that always the particle velocity is in phase with the acoustic pressure for a travelling wave, right. And this is a very important result. This will not happen for other kinds of waves. Once you start getting superposition of waves, you are not going to get this situation. So, that is why we say that this quantity impedance is actually what characterizes the nature of the wave, right. It depends only on two quantities, which is the medium rho 0 and c, but please note that it is not c alone, which when we talked about waves in general without building onto this harmonic assumption, we said that the wave speed is dependent on c, which is a ratio of gamma p 0 by rho 0, right. But now what we are saying is that we are talking about ratio of pressure and velocity, and that ratio of pressure and velocity depends on this quantity rho 0 c, which in fact is square root of gamma p 0 times rho 0. So, as long as this quantity is same, we are going to see that wave propagation effects such as reflection, rarefaction, Snell's law, all of this depends on this quantity rho 0 c rather than anything else. So, therefore, this quantity rho 0 c, which is basically a property of the medium, is a characteristics of a travelling wave. We will see that once you have superposition of waves, we have standing waves for example, then you will not have the impedance given to be in such a simple formula. The impedance will depend upon spatial locations, for example, the impedance will depend upon frequencies, but it is only for travelling plane waves do you have such a simple formula for acoustic pressure divided by acoustic particle velocity. Not only that, we will just preempt a few results that will come much later. Even for other more complicated waves such as spherical waves or cylindrical waves or any other fancy kind of 3-dimensional wave, under suitable approximation, which is to say that if you are really far away from the source, you can say that this impedance term, you can see to it and we will derive that result later on, that for example, in a spherical wave, if you are far away from the source, you will get to say that this impedance of this spherical wave will tend towards this number rho 0 c, and that is why we will say that the spherical wave will approximate the plane wave condition, and that is why we study plane wave in great details, because at least in some approximate sense you can be very sure that this plane wave theory applies to lot of other more complicated situation. But I will end today's lecture with this with emphasizing this fact that rho 0 c is the characteristic impedance of a plane wave. You should associate more importance with the value of rho 0 c, and the sign of rho 0 c you should be able to interpret depending upon forward or backward. Please remember, mathematically it may seem that they are very different because of the plus or minus sign, but if you think in physical parlance, it is actually making sense that the velocity, since the particle velocity will actually change its sign because the direction of the wave has changed its sign. The final point is the pressure and velocity in the direction of propagation of the wave. If you take that to be the definition, then you will see always it is rho 0 c, right. But usually it is best mathematically it is best understood as acoustic pressure divided by acoustic particle velocity. That is the formula that we will pick up from here. The concept of impedance actually get pretty complicated once you have a superposition of different waves. Okay. So, we will leave it here for the present.